Okay, so this is Pauli's identity, which we will demonstrate. It's really easy using component form of vectors. So, and this is the idea. So the idea is that if we have vectors A and B, expressions of the form can be simplified in a rather easy way to give A dot B plus I A cross B dot sigma. So this is a triple product between A, B, and sigma. So now we know that dot products between, let's say, vectors A1 and A2 can be written in component form as A1I, A2I. Okay, so using Einstein's summation convention. And we also know that matrix is sigma. So sigma x is equal to 0, 1, 1, 0. Sigma y is equal to 0 minus I 0. And sigma z is equal to 1 minus 1 and 0 in the off diagonals. So, knowing this, we can also recall that the product of two sigma matrices of two components of the sigma vector. There goes the sigma vector. I use a hat because sigmas are operators, spin operators, or operators in spin space. So these operators are a vector of matrices of the form sigma is sigma y is sigma z. Okay, so and when you multiply any of any of the components of the sigma vector, let's say sigma x sigma y, or sigma y sigma z, or sigma x sigma z, then this product of the components sigma I sigma j can be written as a diagonal plus the tensor Levi-Civita tensor times sigma k. This is a very useful identity that we will use. So now, proceeding furthermore, then we can write what we're hoping to write in the following way. So what we're hoping to do is to simplify an expression of the form using components. So then using components, I can write first that product, this one, AI sigma I, with a different index, bj sigma j. So then I write AI sigma I, bj sigma j. Everything commutes here, so I can just say that this is AI bj sigma I sigma j. Recall sigma I sigma j equals to delta ij plus I eijk sigma k. Please note that this I here, this one, let's do it in blue. This is a complex number, but this I here is just an index, just as j and just as k. Okay, so then using this, a dot sigma times b dot sigma can be written as aibj delta ij plus I e j k sigma k. So we write ai bj delta ij plus I e ijk ai bj sigma k. So now we can see the following. This thing here is nothing but AI BI, and because of the so in Einstein summation form, this is just the dot product, and using the properties of permutation of the indices of this tensor eijk, and recalling that the cross product is an anti-symmetric form of a tensor. So we can just see that first, leaving k fixed, we have in aij, let's say comma k times I bj sigma k. So this is kind of a component of a vector c, a component k of vector c. This is kind of a vector c that's been whose component has been multiplied by sigma k. So in general, this expression here can be seen as c dot sigma. Now, the important thing is to see what is c, and by the definition of the cross product, you can see that when you interchange I and j in this tensor here, then you will pick up a minus sign. So let's do something. Let's do the following. Let's recall that this can be written in this way. So write the unit vectors here. Let's write this in general coordinate form. So write it a1, a2, a3. Then here this is a1, this is a2, this is a3, this is b1, this is b2, and this is b3. See, so that means that the component 1 of this vector a cross b, component 1, which is this, is nothing but this product minus this product. So then a cross b 1 is equal to a2 b3 minus a3 b2, and this can just be written in the following way. This can just be written as a tensor e23 times a2 b3. So in the same way, for the other components of A cross B, for component 2, so let's use purple here. For component 2, so I have this one and this one. Now for the rules of the evaluation of the determinant, which is -1 to the power of I plus j times the times an inner determinant. So this term here is in row 1, column 2. So the -1 to the number of the row plus the number of the column here will be -1, because the summation of column and row index is odd. So then we will pick a minus sign here when we do this multiplication. So then this will look rather like this. This will look as minus A1 B3 plus A3 B1. So this is minus E13 A3 B1. So then in the last component of the cross product here can be written as A1 B2 minus A2 B1. This is equal to A. This is equal to A1 2 A1 B2. And in general, here one can see a pattern that the K component of this cross product is a tensor which has K fixed, has a K fixed and only two of its indices exchange. So the clue point here to see is this. If I have a tensor 1, 2, 3, to produce the E13, then I have to interchange this neighboring ones here, and if I interchange these neighboring indices here, I will pick up a minus sign, so this will be minus E132. Though E23, this part of this tensor here, E23 for component 1, let's do this. If I have the tensor E1, 2, 3, if I just want to see what happens if I just want to pick up index 2 and 3, just be neighbors of each other or being adjacent, then I can do a cyclic permutation of number 1 here, and I just put number 1 here without picking a minus sign, and I will have 2, 3, 1. See, the same thing with 1, 2. If I have E12, which is just shows up in here, there's no minus sign. Now the only time where I pick up a minus sign using this cyclic tensor is when I need to put together indices 1 and 3. So in general, I can say this. In general, I can say the following. Let's just erase here a bit. if I want to write the components of a cross product like this, using this Levi-Civita tensor, so I can do the following. Component 1 is equal to the tensor E2, 3, 1, that at the stake of changing 3 and 2 we become minus sign, so it is perfectly matches the definition of this component of the cross product times A2 B3. A cross B, component 2 is just E. Now this will be at the end, we will have a 2, here we will have a 3, and here we will have a 1. This becomes immediately a minus 1, but when you change 3 and 1, you go back to plus 1. So then this as well complies with the definition for the term for the component 2 of the cross product we're looking at. This is A1 B3, and lastly this third component of A cross B can be written in this way. And then we can say that in general, the K component of the cross product can be written as EIJ K AI BJ. So then, knowing this, we can just go back here and see the following. So let's go back to purple. This term here, what we have here, is nothing but the cross product between A and B. The K component of the cross product between A and B times sigma K. And since I have one vector here, the component K of one vector here, and the component K of another vector here, I can say that this is nothing but the dot product between whatever A cross A cross B gives times sigma. So then, now, finally, after this analysis, we can rather, in a straightforward way, write the following. So let's just erase this, and we can say that A dot sigma B dot sigma is equal to A dot B plus, see that this has the I originally here, so this is I, A cross B dot sigma. So this identity which actually I'm not 100% sure it's called Pauli's identity, but I think it is. So just if it's not, just feel free to post a comment and let me know what you found out. So, Pauli's identity so it will be extensively used in all the other videos that I will be posting for this course on probing condensed matter and open molecular quantum mechanics. So it's important that you know where this identity comes from and how to use it. So pay special attention to the videos on effective action theories. Here we describe pretty much magnetism and lattice dynamics, and this we will use extensively there. And of course, like the place where you would see this more, the place where you will use this more rigorously will be in probably Dirac theory. There you will use it like really often. So then, but this I just finished this video, and just let me know what do you think in your comments.